students, power pattern and normalized electric field is proportional to normalized power is proportional to normalized electric field square. So now this electric field is proportional to sine theta. So normalized power is proportional to sine square theta. So actually what is the meaning of normalized power? Power pattern is observed by changing theta and pi only. That is our focus. In normalized power, we are not bothering about the magnitude term of the power. So sine square theta. So Pn is normalized power. This is also like that only. Actually, average Poynting vector. Anyway, let us not waste our time. Actually, if you take power, then power divided by maximum power is defined as normalized power. Similar to electric field, normalized electric field. So the normalized power means power divided by maximum power. Then only theta term and pi term will be there. But for Hessian dipole, there is no pi term actually. Only theta term is there. Once again, we will, first one is that Pn normalized power versus theta plot for pi is equal to 0. Pi 0 means once again xz plane. xz plane. So here theta value, theta is equal to 0, then normalized power is equal to sine square 0 is equal to 0. Theta is equal to pi by 4. Normalized power is equal to sine square pi by 4. That is equal to 1 by root 2 whole square. That is half. Okay. Theta is equal to 90 degrees. Normalized power sine square pi by 2, that is equal to 1. Theta is equal to 135 degrees, 3 times pi by 4, and normalized power is sine square 3 pi by 4, that is 1 by root 2 whole square is 1 by 2. Theta is equal to pi radians. Normalized power sine square pi 0. Actually, if you see carefully, here highest power is maximum power, this one. Okay, this is maximum normalized power, student. Maximum power is present. Normalized power is maximum means power also will be maximum. This one. This is actually half of the maximum power. Is maximum normalized power is 1 at this location. That means at this angle power is also maximum. This is called half power angle. So half of the maximum power, that is. So that is nothing but maximum power divided by 2. Maximum power is 1 actually. That is why this is called half power angle. That means at this angle power is half. This is maximum power is there at this angle. This is also half power angle only. This one also. Okay, this is also half power angle. So at this angle half power is present. So this is called half power angle. Okay. Now if you draw the plot here, this one x-axis, this one is z-axis. Here angles you write, this is z-axis. Theta is equal to 0 here. Theta is equal to pi by 4. And here vertical angle theta is equal to pi by 2. Vertical angle is always measured from this, student. Theta is measured like this. So this one theta is equal to 3 pi by 4, and this one little bit like this. Okay, no problem. This is theta is equal to pi. You draw this side it is actually symmetric. This is the maximum power. Let us take this as a 1, and half of this power, this is total 1, half of this you take, and half power in 45 degrees direction like this, and here also half power in 45 degrees direction. This much is there here like this. Now you have to draw like this. Similar to this side also you will have symmetric pattern, exactly same. Here now at each and every angle this much length will be there, this much power will be there. Here this much power at this angle, at 90 degrees this much power, like that. This is a maximum power point, maximum power. This one 45 degrees angle here to here, this is half of maximum power. This is also half of maximum power. So this one and this one, they are called half power points. The angle between half power points is called as half power beam width, HPBW, half power beam width. So theta means angle symbol, half power beam width. For Hessian dipole, half power beam width. Actually, first of all, I will write half power beam width. So this is called simply half power beam width. This is also called as angle between half power points, angle between half power points. Okay, then theta FNBW. FN, first null, beam width. This is also called angle between first nulls. Here null means zero value. Null means zero value. Okay. For Hessian dipole, half power beam width is equal to Here na, this angle is 45, and from here to here angle is 135. So 135, this is 135 student, this is 45. 135 minus 45, that is equal to pi by 2 radian. In terms of degrees, 90 degrees. Not for every antenna this one. This is for Hertzian dipole only, not for every antenna, because different antennas have different normalized power equation. So this is for Hertzian dipole antenna. Okay, next, that is 90 degrees. You can see here, at this angle, here you are seeing, here you get first null. Null means 0 actually. So first null angle is 0. This is a second null. That means first null beam width meaning is already there is one null here. Again, after how much angle null comes? To 180 degrees angle, na? So this angle is called as so theta is equal to 0. You have first null. Again at theta is equal to 180 degrees, because sine is 0 whenever sine square, otherwise sine theta is 0 whenever theta is 0, and again sine function becomes 0 whenever theta becomes 180. So that is called here, from here to here, this angle is called actually theta f n b w. So for Hertzian dipole, this value is actually 180 degrees, student. Here you can see, no need to see the diagram, my dear students. You can see here, this is half power point, this is half power point. 130 degrees, this one, 130 degrees, not 130 student, 135. 135 degrees minus 45 degrees, 90. That is the half power beam width. Here one null came. If you want to see the beam width, na, again you have to look for next null. So this is the next null coming. Null means 0, coming at 180 degrees. So this angle minus this angle is called first null beam width. So pi minus 0, pi radians, otherwise 180 degrees. So theta f n b w is equal to pi minus 0, that is pi radian, and here this is for these two are for which antenna? For Hertzian dipole. Okay, next, from these two we got one conclusion. What is that conclusion? Half power beam width is equal to first null beam width divided by 2. So, but this is applicable for every antenna, any antenna. In general, half power beam width is equal to FNBW by 2. In general, for any antenna, this is valid. This is valid. This equation is valid in general for any antenna if there is symmetric pattern. Okay, right. Now actually, what is the procedure to find the first null beam width and half power beam width for any antenna? You have to find electric field equation. Then take the square of the electric field. then normalize that, then you get normalized power. Then no need to draw the diagrams. Simply make this table. You see at which angle highest power is there. Then at some other two angles you will have half of that power. Then take the difference between them. You will get half power beam width. Similarly, at one angle you will get 0. Then again, after how much angle you are getting 0, you see, take the difference of them. Then you get FNBW. Otherwise, if you get half power beam width, you take 2 times of that, then you get FNBW. So no need to draw the diagram and no need to confuse. But in exam, if already diagram is given, then from that you can also recognize the half power beam width and FNBW. Okay, right. Now students, you see this one, P2 by P1 power ratio in dB is equal to 10 log 10 P2 divided by P1. Actually, if you want any power ratio in decibels, then you have to take 10 log 10 power ratio, because inside logarithm you should not have any unit. Maybe one line I am telling, why to take decibels? Because human beings hear in decibels. आदमी लोग है सुनने के समय में वो डेसिबल्स में सुनता रहता है, एक्चुअली बिल्स में सुनता है. बिल मतलब log of P2 by P1 is called as a bill. Actually multiply with 10, then decibel, that is. Anyway, that is one thing. Second thing is, for example, power ratio is 10 to the power 9. It is huge number. But once if you take log, then simply it becomes very small number, 10 power 9, that is equal, it becomes 90. So it compresses the numbers actually. That is one thing. That's why you want to take logarithm. But if you want to take logarithm, there should not be any units here. Sometimes you have to represent only power in terms of decibels, but power ratio is not there. Then power has units. Then what to do? If you want to take power in decibels, you have to remove the units. There are different ways. If that power is in watts, actually it is in watts, then divide that power with 1 watt. Then take 10 log 10. So then this power becomes in decibels. So to remove the units of this power, you have divided with 1 watt. So after removing the unit, you have taken 10 log 10. So then you get decibels, but you compared with 1 watt. So 10 log 10 taken, that is why you call decibels. But compared with 1 watt, you call it as dB watt. So you found power in decibels, that means 10 log 10 you have taken. But after comparing with 1 watt, you have done that. Okay. Next one. Sometimes if these power calculations are in microwatts, then you will be comparing with 1 microwatt power here. Then you will call it as a dB mu W. Mu means micro. Simply, if powers are in milliwatt, then you will be comparing that power with milliwatt. You divide with 1 milliwatt. Then you will take 10 log 10. Then that is called decibels in milliwatt. So that is called power in dBm W. If you don't have patience, simply you say dBm. So dear students, now I am writing here second point, P power power in dB is represented by comparing with 1 watt power, with 1 watt power, then okay, right, because we will write here like this. So single power in decibels by comparing with 1 watt, that is called dBW, is 10 log 10 P divided by 1 watt. Okay, like that it is. So 10 log 10 P means that is dB and compared with 1 watt. Similarly, if powers are in milliwatt range, then we will be comparing with 1 milliwatt. Okay, so power in decibels means 10 log 10 you have to take 10 log 10, but this has some units. How you remove the units? If it is in milliwatt range, compare with 1 milliwatt, then milliwatt gone, you get dBmW here. That means you found this power in decibels by comparing with 1 milliwatt. This is also in some books there are dBm. W is not written like this. So power in decibels by comparing with 1 milliwatt. Actually, I am not writing all this story. It depends on you. If you want, you can write. By seeing this, you can understand. Okay. So you can see here the meaning is power represented in decibels after comparing means dividing you right, after dividing with 1 milliwatt. That is the meaning. Similarly, what is this? Power in decibels after dividing with 1 watt, like this. Okay. For example, question: given power is equal to, you say 10 dBW, decibels compared with 1 watt. Find power. Now power in dB watt is equal to 10 log 10 power, okay, divided by 1 watt. I wrote this side as a power so that you will not be confused. Now it is given as, this is formula, it is given as here 10, that is equal to 10 log 10 power divided by 1 watt. 10 cancel, then power divided by 1 watt is equal to, this is 1, so 10 power 1. That means given power is actually 10 power 1 means 10 watts power is there. So that is the meaning, dear students. Okay. So even if a power 10 watts is given, then you want in dBW, put here 10. So 10 watts by 1 watt you get 10. Log 10 base 10 is 1. 1 into 10 is 10. So you get 10 dBW, like this. Right? Right, friends. Okay. So students, you see here differential solid angle. Differential solid angle. Symbol is omega is a symbol here used. Not this is not ohm, student. That is, this is not impedance. Here symbol is used. So many concepts now, that is why symbols are repeated. So omega is solid angle symbol. D omega is a differential solid angle symbol. So differential solid angle d omega is defined as d omega is equal to ds in spherical coordinate system in AR direction divided by r square. In spherical coordinate system in r direction, ds is actually r square sine theta d theta d pi divided by r square. So r square cancel. So ultimately differential solid angle is sine theta d theta d pi. Actually here d theta is differential vertical angle, sine theta d pi is differential horizontal angle. Here you have seen that r theta pi and this is dr. Here differential length is r d theta. Here differential length is r sine theta d pi. Now if you substitute r is equal to 1, then r is equal to 1 you put, it becomes d theta, then it becomes sine theta d pi. You multiply them, this is a differential vertical angle radian multiplied with differential horizontal angle radian. Radian multiplied with radian square, that is also called as steradian. Symbol is SR. So differential horizontal angle. For example, any differential angle na. For example, vertical differential angle theta, it gives one surface actually surface. But differential horizontal angle and differential vertical angle, they give the volume. They give the volume. Volume other name is solid. That is why that is also called as a solid angle. So for example, I will show you here. Here this is a differential horizontal angle. Let us say 1 degree is there horizontally like this. Now here you did this, you get surface here, surface. Now similarly, like this you take differential vertical angle 1 degree you take or 1 radian. 1 radian you take. So with this also you get surface here. 1 dimension surface you get, 1 angle. Now you take differential horizontal angle and differential vertical angle like this. Now here you get the volume in between them. Here horizontal angle 1 radian is there, and here vertical angle now from this one to this one. So vertical angle also 1 radian is there. So that means here you have volume here. In that volume, here if you put antenna like this, then this antenna in this volume, how much power is radiated? Then that is called watt per steradian. So in this volume, watt per steradian, we'll see that steradian means two-dimensional angle multiplied with angle, vertical angle multiplied with horizontal angle, right? So this is the differential solid angle equation. The unit is steradian. Simply it is called as SR. This one. Now for complete sphere, what is the solid angle? That is 4 pi. So total solid angle of a sphere is integral sin theta d theta integral d pi pi from 0 to 2 pi theta from 0 to pi. So you get this is minus cos theta and theta from 0 to pi, and this one is pi varying from 0 to 2 pi. So this becomes 2 multiplied with 2 pi, so that is equal to 4 pi steradian. So for total spherical region, the total solid angle is 4 pi steradian, 2 into 2 pi. That means, have you seen, student, for a sphere, this is area by r square. For this omega is area by r square. For a spherical surface, area is 4 pi r square divided by r square. You get 4 pi. Okay, steradian. Now, dear students, let us talk of radiation intensity. Radiation intensity. Symbol is U, theta, comma, pi. Actually, this radiation intensity symbol is U, theta, pi. Now, first I will tell you something. Then we will write that definition. Radiation intensity U, theta, pi. Here you can see by symbol itself. You can see that means how radiation changes with theta angle, vertical angle, and horizontal angle. That symbol itself gives some information to you. Now you keep watching here. For example, you students know that average Pointing vector is equal to, in uniform plane wave, half electric field square divided by eta power flow direction. Until now you have seen this is also given by power density and unit vector in direction of power flow. You students know that, sir, why are you using this formula? This is related to uniform plane wave. You may ask question. I told you already, this transmission line is there, and you are giving a FM signal, radio mirchi signal, that is going through this transmission line. Whatever goes in the transmission line, same is radiated by the antenna. So this is uniform plane wave. Antenna radiates into the air medium. After radiation, it goes here. That is called uniform plane wave. So that is why same formulas are used. So whatever signal travels on transmission line, same is radiated here. So that is why formula is same. Anyway, now I am telling you, this is the average Pointing vector. Unit is actually watt per meter square, students. Now, for average Pointing vector, half electric field square divided by eta. If EM wave travels in r direction, radial direction, then this is the power density PD. I will write simply power density PD A r cap watt per meter square, students. Now, what is the power radiated by any antenna? Then average Pointing vector multiplied with ds bar. That is nothing but here. Shall I write like this? This one, modulus of average Pointing vector. What is modulus of average Pointing vector? This one, multiplied with AR cap. See here, power density and this one all are same. So modulus of average Pointing vector means this one only, half mod e square eta. So modulus of average Pointing vector into AR cap. So I will write here like this. This one, P AVG bar can be written as modulus of average Pointing vector AR cap. DS bar in AR cap direction is r square sin theta d theta d pi ar cap. Now ar dot ar is 1. So double integral p avg bar multiplied with r square, then sin theta d theta d pi. So this term, tell me what is the what is the symbol used for this d omega? What is the unit of that? Steradian. And what is this? This is power, actually, power. So this is d omega and unit of this is steradian. And you can understand that I will write this is unit of this is steradian. Then what should be the unit of this, my dear students? Actually, this is watt per meter square multiplied with meter square gives watt. Okay, so this is watt actually, and this is steradian. You have seen the symbol given for this is d omega, differential solid angle. This is steradian. Then what it should be? What is the unit of this one? Watt per steradian. It should be that much. It should be that unit, because you want watt na, this is steradian na, then watt per steradian should be there. Steradian cancel, you get watt. That means this term is defined as u theta pi, and this term is defined as d omega, and unit is watt actually. So this is the radiated power, and this is called radiation intensity. Unit is actually watt per steradian, and multiplied with steradian, then steradian cancel, you get watt here. So power radiated is in watts. My dear students, here u theta pi is named as radiation intensity. You students can understand here, for example, power density is proportional to 1 by r square, or otherwise electric field is proportional to 1 by r, and electric field square means 1 by r square. So average Poynting vector is proportional to 1 by r square. 1 by r square multiplied with r square term is gone. That means if electric field is a function, if you solve electric field in spherical system, electric field is a function of r theta pi, then electric field square multiplied with r square, r term gone, then remaining terms are theta pi. That is why it is symbolized like this. So radiation intensity is a function of theta and pi only, because average Poynting vector is a function of r theta pi. Average Poynting vector is proportional to 1 by r square, and multiplied with r square, radius gone, only theta pi are there. So this is the radiation intensity. Now concept also came, all formulas came. Now first one, radiation intensity is defined as u theta pi is equal to average Poynting vector multiplied with r square, or otherwise power density multiplied with r square. Unit is watt per steradian. Symbol is u theta pi. That is one formula. Second formula is, given radiation intensity equation, then power radiated is given by, this is the formula. Okay. Now I will write those things there. Here, radiation intensity is defined as u theta pi is equal to average Poynting vector magnitude multiplied with r square. That is nothing but power density multiplied with r square. Unit is watt per steradian. Okay, right. You have to remember the formulas. Now imagine, you have to imagine how to calculate radiation intensity. Answer. Here are the formulas. Already I wrote these formulas. In the question, electric field is given. Take electric field equation square divided by eta half. Then you get the magnitude of the average Poynting vector. Then multiply that with r square. Then you get the equation of u theta pi. That is one way. Second way, they have given power density. then multiply that power density with r square, then also you get the equation of u theta pi. So there are two ways to find the u theta pi. So here PD is power density, that is in watt per meter square. This is one formula is over. Second one, you may ask the question, what is the significance of this? Answer is in the units of this. For example, u theta pi is equal to 10 watt per steradian meaning is you take 1 radian multiplied with 1 radian, then steradian is 1 radian square. That means you take 1 radian horizontal angle, then 1 radian vertical angle, then here one antenna is there, then that antenna radiates 10 watts power in the volume which is bounded by 1 radian horizontal angle and 1 radian vertical angle. That is the meaning of that. So for given horizontal and vertical angle, how much power is radiated? So that is given by the radiation intensity, students. Okay, this is one formula. Second formula, given radiation intensity, u theta pi, then power radiated by the antenna is power radiated is equal to double integral u theta pi d omega. D omega means sin theta d theta d pi. So the units watts. Now I told you u theta pi is watt per steradian multiplied with steradian. Unit is this one. Okay, this is also formula. You see this in examination. In examination questions, we have to use this. They give radiation intensity and they ask you to calculate the power radiated. Then put the radiation intensity equation here. Then d omega. D omega means I wrote here. You have to remember that one. Sin theta d pi. Okay. Next, one more formula. Average radiation intensity formula is required. For that, you have to apply your common sense. You have to use like network theory or signal systems. Every student knows if x of t is some function, then x function average value is always constant, that is, average value is constant. Then similarly, u theta pi is variable, then u average value is definitely constant, dear students, constant. So in this formula, if you substitute power radiated is equal to, in this formula, in place of variable, you substitute average radiation intensity, then you will get the answer here d omega. So u average, actually average value means constant, it comes out. So if it comes out, then u avg double integral d omega. So double integral d omega is actually sin theta d pi. So theta varying from 0 to pi, pi varying from 0 to 2 pi. Already we have derived that there total solid angle is 4 pi. So that means power radiated is equal to average radiation intensity, and this value is 4 pi. So average radiation intensity is equal to total power radiated by the antenna divided by 4 pi. So that is the formula of that one. This is the way you get this one. So here you write here average radiation intensity, average radiation intensity is U AVG is equal to total power radiated by the antenna divided by 4 pi. So this is watt per steradian. This is the formula. Okay. This is also called as a average radiation intensity of an isotropic antenna. This one. Okay. Average radiation intensity is actually for any antenna you can define this. Average radiation intensity of any antenna is equal to total power radiated by that antenna divided by 4 pi watt per steradian. Right, students? Now, once if you know these formulas, you are going to talk of directive gain. In name itself it is there. Directive gain. That means direction to direction gain is going to change. Direction to direction gain is going to be changed. So different directions, different gains are present. So that is called directive gain. Okay. Directive gain, that is the another definition. So directive gain. Actually, gain symbol means G, suffix D means directive. This is also a function of theta and pi. That means if vertical angle changes, horizontal angle changes, then directive gain value is going to change. You are saying gain means there is no unit for that. Okay. So this directive gain is a measure of radiation intensity in particular direction. So it is a measure of radiation intensity in a particular direction. So dear students, directive gain gives the radiation intensity in particular direction. So it is defined as directive gain is defined as the ratio of radiation intensity in any direction divided by average radiation intensity. So directive gain is defined as the ratio of radiation intensity in any direction or otherwise given direction, you can say any direction, and average radiation intensity. Average radiation intensity. That means actually radiation intensity in any direction is u theta pi. Average radiation intensity. This is defined as directive gain. This average value is constant, but it is a function of theta pi. So that is why it should be a function of theta pi. Then u theta pi, already you have seen here UAVG is power radiated divided by 4 pi. So that means that is so this is nothing but this is 4 pi and u theta pi divided by power radiated. So what is the unit? it is unitless because it is a gain. So you have to remember this one. Then once if you are reading this formula, inside your memory you have to imagine how you get questions in exam. Whatever parameters are there, they may give radiation intensity, and then from that only you can find average radiation intensity and the ratio you take. Or otherwise in examination they give u theta pi, and once u theta pi is given, they will ask you to find directive gain. Yes, you can calculate from this. Here you substitute that u theta pi, then you have to calculate power radiated. Given u theta pi, then power radiated is formula is here. From that you will be calculating. So in this way, dear students, this directive gain tells you how much radiation intensity is there in a particular direction divided by average radiation intensity. Okay. So this gives actually directive gain. Actually, directive gain is a measure of concentration of power radiated in particular direction. So this one you have to remember. This is just for your information. Then directive gain is a measure of concentration of radiated power or power radiated in a particular direction. For example, I will tell you student here, one antenna is there like this. This antenna is given, for example, 10 watt input power is given. 10 watt power is given for this antenna, or otherwise it radiates 10 watt. Assume losses of the antenna 0. Then if you give 10 watt power, it radiates 10 watts. So it radiates like this, let us say. Now direction to direction, for example, in this direction power radiated is this much. So power radiated is this much at this direction, u theta pi radiation intensity. So in this direction radiation intensity is 0, in this direction 0, in this direction 0, in this direction less value, little bit more value. In this direction maximum radiation intensity is there. So direction to direction radiation intensity changes. Then you take average value of this one. So if you take average value of this one, or otherwise there is another antenna here, another antenna is there here, second antenna. For this antenna also we will give a second antenna, this one, second antenna. For this also we are giving 10 watts power. So 10 watt power is there for this also. We are giving input power. Assume both antennas have both antennas are lossless antennas, and for this also 10 watts power is given, for this also 10 watts power is given. That means for both antennas same power is given. Assume this black antenna is a directional antenna, that means it radiates only in particular direction. Assume that this is a blue one is isotropic antenna, it radiates equally in every direction. So then this blue antenna is going to radiate like this. So it is this one is isotropic antenna. Iso means same, tropo means direction. So it isotropic antenna means it radiates same power in every direction. So now this antenna has average radiation intensity, because on an average it is radiating equal power here. It is symmetric actually. It is symmetric here. Okay, it is symmetric. So on an average it is radiating same power in every direction. It is called as average radiation intensity. It has this one, See here, two things are there. Listen carefully. This is directional antenna, black one. For that 10 watts power is given. But the characteristic of this antenna is it radiates only in particular direction, because that is the requirement. For example, here earth, this one earth antenna, here satellite is there. Satellite is moving like this here, and satellite is moving like this. Then every time earth also rotates. Then if earth rotates here, satellite also will be rotating in same way. So this antenna, every time it has to radiate in this direction only. Okay. So in this way, we need directional antennas. Now same directional antenna, you remove this power, and here you distribute that equally here, then that average value becomes again this one only, this blue one only. So you take one isotropic antenna, you give same power 10 watt, you take one directional antenna, you give 10 watt, then this directional antenna is radiating in this direction, and then isotropic antenna is radiating here like this, equal radiation intensity in every direction. Now you can call this pattern as a radiation intensity of isotropic antenna, or otherwise average radiation intensity of same antenna. I told you, you remove this power and on an average you distribute here, again you get average value this much only. So here I am writing this isotropic antenna, this one, second antenna, this one, sorry, second antenna, this one, that is isotropic antenna. Okay, so both are given same power, input power. Now U average has two names: average radiation intensity of any antenna, or otherwise average radiation intensity of isotropic antenna. Now, do you know then what is the gain of this one? What is the gain of this isotropic antenna? So, gain, directive gain is equal to radiation intensity in any direction divided by average radiation intensity, that is equal to 1 for isotropic antenna. For isotropic antenna, you know why? For example, for isotropic antenna, radiation intensity in this direction is u theta pi, you say, then that is exactly equal to U average value only for isotropic antenna. That one. So for isotropic antenna, radiation intensity in any direction is equal to the average radiation intensity. So that is why directive gain is 1. So for isotropic antenna, radiation intensity in any direction, radiation intensity in any direction, that means that is u theta pi, is equal to the average radiation intensity, because it radiates equally. It radiates equally in all directions. It radiates equally in all directions. Okay. But for this antenna, radiation intensity in this direction is u theta pi this much. Divide with average radiation intensity, that is this one. Then directive gain in this direction is more. For example, here you see this much, this much, this much, almost 3 times more for this directive gain. So in this way, for this black antenna here, in this direction, maximum radiation intensity is there, dear students. Total here 3 things are there. In this direction, maximum radiation intensity is there, and in any direction this radiation intensity is variable, that is u theta pi. And again, average radiation intensity of this antenna is UAVG is again constant. So 3 are there. Maximum radiation intensity, this is also constant, and average radiation intensity, that is also constant. And if direction changes, then direction to direction radiation intensity changes. For example, functions they are seen like this. After some time you will see while solving questions 4 sine square theta cos pi, like this it is. So that function, then theta pi changes na, then this keep changing. Then maximum value is 4 actually. So dear students, maximum radiation intensity divided by average radiation intensity is defined as a directivity. Directivity is more means it is radiating in particular direction. That is the meaning. Directivity is more means in particular direction gain is very high. That means in the direction of its radiation, actually this antenna is manufactured to radiate in this direction highest, because here satellite will be roaming. That's why. So that is called directivity. Okay. Generally narrow beam antennas have very high directivity. For example, here this isotropic antenna radiating power here equally. Now what I do, if I supply that power to directional antenna, it supplies power to this volume. If it is highly directional antenna, then that goes power like this pencil beam, that is called as. For highly directional antenna, na, like this, na, you take one antenna, okay, pencil beam, it goes for larger distances. If that is directional antenna, like this it goes. That is called pencil beam. For this, directivity is very high, because it is sending power for longer distances. It is targeted power, pencil beam, that is called as. So dear students, what is directivity? Directivity is defined as, symbol is capital D, maximum radiation intensity divided by average radiation intensity. That means maximum radiation intensity U max by U average is defined as directivity. That means here numerator maximum, that is called GD maximum directivity. That is also 4 pi U max by power radiated formula. Okay. So next one is directivity. Directivity or maximum directive gain, that is called GD max. This one, GD max. So directivity is equal to GD max, that is defined as maximum radiation intensity divided by average radiation intensity. that is equal to 4 pi into u maximum divided by u average value. It is defined like this. This is a definition. So for this, there are if you want theory, you can write like this. The directivity D of an antenna is the ratio of the maximum radiation intensity is the ratio of the maximum radiation intensity to the average radiation intensity. Okay, and one more formula is there for this directivity. Another formula is there, 4 pi divided by half power beam width in plane 1 multiplied with half power beam width in plane 2. So this is another formula. That means theta half power beam width actually this is also called as beam solid angle, student. If you want, you can write that. 4 pi divided by beam solid angle, the symbol is called as omega A. Actually omega means solid, so here A means you can say angle, solid angle, that is beam solid angle. Okay, this is nothing but this one only. So theta half power beam width, 1 means half power beam width in, you can say, horizontal plane, half power beam width in one plane, Actually student, half power beam width in one plane means this radiation pattern is like a balloon. Balloon has volume, that has width also, that has height also, like this, na? Balloon is there, students. You can see here balloon is there like this. Actually it has height also, but it has width also. In height direction, half power beam width is like this. So this is maximum power and this is maximum power by 2. So maximum power by 2. This is also maximum power divided by 2. Then this is called as half power beam width in plane 1, vertical plane. Then 90 degrees to that vertical plane, in this direction how much beam width is there, half power beam width, that is half power beam width 2. But in general, if this pattern is symmetric pattern, then theta half power beam width in vertical plane and theta half power beam width in horizontal plane both are same, then you get theta half power beam width whole square you get. But for some antennas, for example, you take a balloon and you compress that balloon in horizontal direction, then in vertical direction it will have more beam width, in horizontal direction it has less beam width. Some antennas have radiation pattern like that. That is not your problem, that is given in the question. So always horizontal plane is there and vertical plane is there. So in horizontal plane, what is the half power beam width? You can say one is horizontal plane. One plane means you can take half power beam width in one plane. That means you can take like example horizontal plane. Okay. So theta half power beam width 2 means that is in second plane. Half power beam width half power beam width in a plane perpendicular to first one. That means whatever is this one, perpendicular one. That means, for example, if you take this horizontal plane, then this is a vertical plane. Vertical plane, half power beam width. So both are in radians here, students. This is also radian. This is also radian. Because here radian, radian, radian. So I am writing here, it is in radian. And it is also in radian, student. But if they give in degrees, for example, pi by 4 degree, then that you write that actually they give in degrees, 45 degrees they have given. You write pi by 4, what is the problem? If they give 90 degrees, you write pi by 2. Pi by 2, like that. Now, here this omega A is equal to theta half power beam width in one plane multiplied with theta half power beam width in second plane. So this omega A is called as a beam solid angle. Beam solid angle. I was telling you, vertical angle multiplied with horizontal angle, you get a volume. Volume other name is solid. So that is why that is called solid angle. So dear students, this is called beam solid angle. This is omega A. So this is a beam solid angle. I am telling you this is in radian, this is in radian. Otherwise you will get a mistake. You will get wrong answer. So dear students, if they give this, I told you 30 degrees, then you write pi by 6 in radians. One more formula is there that in angle, you try to reduce the number of formulas. No use. If they give degrees, for that separately no need to remember. Because if they give degrees, you know how to convert into radian. Very simple. Now, after reading these formulas, here some standard data is there. Note. Okay. First one. The range of D directivity. The range of directivity is 1 and less than or equal to D less than or equal to infinity. You know that directivity 1 is for isotropic antenna. For isotropic antenna. This is not possible, this value, for highly directional antenna. It is only theoretical discussion. That means meaning is that antenna sends power up to infinity distance. That is actually not possible. That is you say ideal discussion, that is. Okay, second point. D is equal to 1 for isotropic antenna. For an isotropic antenna. So it is the smallest value of D directivity. Next point, for Hedgian dipole antenna, for Hedgian dipole antenna, directivity is equal to 1.5 student. Next, fourth one, for lambda by 2 antenna, directivity is equal to 1.64. Okay. Then for these are all standard questions, student. For lambda by 4 monopole, for lambda by 4 monopole, near ground is D is equal to double of this one, that is 3.28. These are standard values. So these are all standard. Okay. If you want, I will tell you for this. For example, rough work I am doing. Rough work, student. I told you to remember for Hedgian dipole, you should not do unnecessary derivations. You are doing unnecessary derivation, no? You will be losing interest on the subject. So what is required for exam, you have to see. Rough work for Hedgian dipole, no? I told you H pi s is equal to I naught dl sin theta, then 4 pi j b, this one j beta divided by r, then e power minus j beta r, I told you. Then electric field is equal to, dear students, eta into H pi s. You have to multiply this with eta. Then average Poynting vector is nothing but half into modulus of e square into eta naught into what do you say, eta naught or otherwise eta multiplied with ar cap. Okay, now that is nothing but half into modulus of electric field whole square is nothing but this electric field value eta into I naught dl multiply with this sin theta j beta divided by r. You take modulus of this, then no need to take this one. Then j also no need to take, that is divided by 4 pi. So I naught dl sin theta divided by 4 pi beta by r, you have to multiply with eta. Okay. Now that is equal to half into electric field square means eta square I naught square dl square. So sin square theta divided by 4 pi square and beta square by r square, and eta was there here. So this eta cancel. Then modulus of average Poynting vector gives actually, so 1 eta remains, no? So eta I naught square dl square sin square theta, then 4 pi whole square, 2 is there, and beta square by r square. Okay. Radiation intensity is defined as modulus of average Poynting vector multiplied with r square, right? You have to remove r square from this, student. That much only, student. Remove r square from this. You have multiply with r square means r square gone. So eta I naught square dl square sin square theta beta square 2 times 4 pi whole square. That much only. So this is the formula of radiation intensity for the Hertzian dipole antenna. Now directive gain is equal to 4 pi u theta pi, this one, divided by power radiated. Now what is power radiated? Radiation intensity then d omega. That is nothing but double integral. This is the radiation intensity. So you take that eta I naught square dl square sin square theta beta square 2 times 4 pi whole square, d omega is sin theta d pi. That is the radiated power. That means radiated power is equal to eta I naught square dl square and beta square 2 times 4 pi whole square. This is all constant, na? Then integral sine cube theta d theta integral d pi. So what I will do, I will take this ratio now. GD of theta comma pi is equal to 4 pi, then u theta pi is this one. Okay. So eta I naught square dl square sine square theta, then beta square divided by 2 times 4 pi whole square. Then what else is there? 4 pi into u theta pi divided by radiation, this one power radiated. So eta I naught square dl square beta square 2 into 4 pi whole square, and then integral, okay, this much. This is equal to GD of theta comma pi, this is. Okay. Now integral sine cube theta d theta integral d pi is there. Let it be like this. Ultimately, student, here you can see I am writing this sine square theta here, then beta square is there here. This one, this one. This one same. Eta I naught square dl square beta square. Eta I naught square dl square beta square. 2 4 pi or 4 pi square. 2 4 pi square. This gone. If this goes, no, then you can see GD of theta comma pi is equal to 4 pi divided by, this is integral, little smaller I will write. So 4 pi divided by integral sine cube theta d theta, and theta varying from 0 to pi, integral d pi, pi varying from 0 to 2 pi into sine square theta. You calculate this integral 4 pi divided by this one, you get 1.5 sine square theta. You get GD of theta pi for Hertzian dipole, 1.5 sine square theta. This value becomes 1.5 sine square theta. So for Hertzian dipole antenna, directive gain is 1.5 sine square theta. Now maximum directive gain means GD max. Whenever theta is 90 degrees, then maximum value is 1.5 into sine square 90, that is 1.5. In that way you got this one. Okay, GD max. GD is this one. GD max means maximum value of directive gain when theta is equal to 90, 1.5 sine square 90, that is 1.5 you get. So this is the procedure. This after doing this much derivation, you are remembering this. There is no use of that, no? Wastage of time only. So this is standard data written here. Similarly, for lambda by 2 antenna also, same procedure you do. Already you have remembered magnetic field equation for lambda by 2. So you get this one. Some function you get. Then after that, directivity 1.64 you get. Okay, right. So dear students, for example, if you want directivity in decibels, then what you do? Actually, it is a directivity power ratios now. So you have to take 10 log 10 D you have to take. For example, directive gain also, if you want in decibels, then you have to take 10 log 10 GD you have to take. Okay. So wherever power ratios are there, then you have to take in decibels 10 log you have to take. Okay. This one. Right. So here we have to talk of power gain. Symbol is GP, power gain. Okay. So for example, students, here one transmission line is there like this. Now you have given power to the antenna. For example, horn antenna, I told you, you will be opening the mouth like this. So if you take this entire system as an antenna, just this is the connection which you give for antenna, you take this as a antenna. So if you take this as an antenna, actually this is a antenna. Okay. Now for this antenna, you will be giving some power input, then it radiates some power, so that is called power radiated. Okay. Now this antenna has some power loss also. Power loss also. So here it is like this: power can neither created nor destroyed. So power conservation. Total input power is equal to power loss plus power radiated. So this is the equation number 1. For example, if In is the input current, In is the input current. So then uh, if In is input current to the antenna, then RL is loss resistance of the antenna. If the RL is loss resistance of the antenna, okay, and R radiation is the radiation resistance of the antenna. So radiation resistance of the antenna. So then automatically power loss is equal to half into maximum current is In square here, RL. Okay, this is equation number 2. Similarly, total power radiated is equal to half into In square radiation resistance, that is 3. Now you can substitute 2 comma 3 in 1, you get a total input power. Okay students, so put 2 comma put equation 2 comma 3 in 1, then you get input power actually. So P in is equal to half into In square RL plus half into In square radiation resistance. Okay, this is equation number 4, let us say. Now actually discussion is like this student. You students know that directive gain is defined as 4 pi into radiation intensity in any direction divided by power radiated. This definition has some issue with this. This has some issue. You see, for example, I asked one student to go to the market and antenna 1, and then that in the market that shop fellow shown two antennas. He told that this also, if you give 10 watt here, then this was radiating 10 watt. So this is P in actually. Then power radiated is 10 watt, it is lossless antenna. Then another antenna is shown, 100 watt is given. Out of 100 watt, power radiated is only 10 watt. Now that student selected this antenna for the practical purpose, that is useless antenna, because if you are giving 100 watts, it is completely 90 watts lost here, only it is radiating 10 watt. If you see only radiated powers, then you feel both antennas good. So that means in the directive gain, power radiated is taken. That means directive gain of this antenna and this antenna, so will have power radiation same. That is why this definition, directive gain definition, is not completing the antenna property. That is why you have to consider power loss also, because some antennas have so much loss. So you have to give new definition which has power loss also. You have seen that input power is a combination of radiated power and power loss. In the definition, if you take input power, while defining gain, if you take input power, then that will be more meaningful. So that definition is given by taking the power input, that is called power gain, that is defined like that. So in place of radiated power, if you take input power, then that gives power gain definition, dear students. So power gain has input power in the denominator, but directive gain has radiated power in the denominator. So anybody ask you what is the difference between directive gain and power gain? Directive gain does not consider power losses. Yeah, then power gain GP, G means gain, P means power. Power gain considers losses of the antenna also. So dear students, now power gain GP, G means gain, P means power, is defined as is defined as Gp is equal to 4 pi into radiation intensity in any direction divided by input power. So this is equation number 6. Now you have to remember this one. Okay, students. Now this is the definition of power gain. So power gain considers losses of the antenna also. So gain considers power gain considers losses of antenna also. So this is more meaningful, student, right? Now after discussing this power gain I have discussed here, now we are going to define radiation efficiency. So radiation efficiency, that is another parameter, radiation efficiency. So the symbol here eta is the efficiency symbol, it is not intrinsic impedance. Eta means efficiency symbol, so radiation means suffix r. So radiation efficiency symbol is eta r. R means radiation, eta means efficiency, here radiation efficiency, dear students. Now radiation efficiency is continuation. Radiation efficiency is defined as the ratio of power gain and directive gain. So that is GD. So eta R is equal to power gain divided by directive gain. So that means if you write these formulas here, power gain is 4 pi u theta comma pi divided by power input. So this is 4 pi u theta pi divided by power radiated. So that is nothing but it goes top side, power radiated divided by power input, that is nothing but power radiated is half in square radiation resistance divided by this one is half in square radiation resistance plus loss resistance. You have seen in this formula P in is half in square is common, RL plus radiation resistance. Here I in is maximum input power, that I was calling earlier as I naught or otherwise IM. So half in square cancel. Ultimately you get R radiated plus RL. So I am putting this in the box now. So this definition you see, okay, this power gain is defined like this definition. So now power this one, not power gain, radiation efficiency. Radiation efficiency is defined as ratio of power gain and directive gain. And after that you got one more formula here, power radiated divided by power input, you got here power input. So that is equal to once again radiation resistance divided by radiation resistance plus loss resistance, you got RL. So this is the formula you have to remember, dear students. Actually there are three ways to calculate. Power gain, directive gain known, then also you can calculate. Radiated power, input power known, then also you can calculate. Radiation resistance and loss resistance known, then also you can calculate. So if you want radiation efficiency in percentage, then radiation efficiency should be multiplied with 100, students. Okay. Now here what do you say, for lossless antenna, for lossless antenna RL is equal to 0. This is 0. If this is 0, radiation by radiation, this is 1. That means for lossless antenna, power radiated is equal to power input, or otherwise direct to gain is equal to power gain, or otherwise radiation efficiency becomes 100%, but there is no antenna which produces zero loss. That is just a theoretical discussion. For lossless antenna, RL is equal to 0. That implies eta R is equal to 1. That means direct to gain is equal to power gain, and also power radiated is equal to power input. That means it radiates total input power without loss. So these are the, what do you say, these are the equations valid for the lossless antenna, right, students? So they ask these equations also in objective question for lossless antenna. So for lossless antenna, that means if you see percentage, that is 100%. You have to multiply 1 into 100 gives 100%, dear students. Okay, right. Now here one more thing. If you want actually this power gain in decibels, once again you have to take what do you say, 10 log, because you can see power is there visible here. Power visible means automatically that is 10 log you have to take. So power gain, this is not actually a note. So power gain, not power gain in decibels, na G means gain, P means power. Decibels is equal to 10 log 10 GP. Okay, this is one thing. Second thing, for parabolic reflector antenna, for parabolic reflector antenna. Actually, these types of antennas are there. Mostly they are covered by the Mr. Naveen because it is allotted like that there. So for parabolic reflector antenna, means it is like this, dear students, like this. Parabolic mouth is there. So this is radius and this one is called diameter. Okay, this one is called diameter. So D is equal to 2A. So here D is diameter. So A is radius. A is radius, dear students. Now for this power gain is equal to here pi square D by lambda square K. So where K is illumination efficiency. K is illumination efficiency. K is illumination efficiency. Actually, practical values of K is 0.65. Then after substituting 0.65, you get this is 6 D by lambda whole square. You get for illumination efficiency, K is equal to 0.65. This is generally practical value. This you remember, dear students. So actually, this GP is a power gain of this one. Now this GP is proportional to 1 by lambda square. Of course, it is proportional to D square. 1 by lambda square is there. Now lambda is proportional to C by F. So it is proportional to frequency square also. I will write like this separately. GP is proportional to 1 by lambda square, and GP is proportional to 1 frequency square. So it is proportional to frequency square, and also GP is proportional to diameter whole square. You can write this one, and again no need to write this one. Okay, that is the observation. Now for this antenna, half power beam width, half power beam width is equal to 70 multiplied with lambda by D, and no need to remember the FNBW. So FNBW is first null beam width is 140. You know that, dear students, 140. Okay, you remember this one, that is more than enough. So for parabolic antenna, generally power gain is this much 6 into d by lambda square, and where k is illumination efficiency, this is general formula, and for practical purposes that k is 0.65 practically that value. Okay, so dear students, you note down this one. This 70 is a number now, so actually it is in degrees actually. Okay, degrees. This is also in degrees, dear students. This is in degrees, not in radians actually, right? Now let us talk of antenna array. So antenna array. So basically antenna array is nothing but array means group. Antenna array means group of antennas. So that is nothing but antenna array means meaning is a group of see students, array means a group of antennas. Okay, so this group means it is called array, group of antennas or otherwise antenna array. So here you see the situation, but here listen the terminology carefully students, so that while solving the questions you need this terminology what I am going to use here. You have to listen carefully. First you take this axis as a z axis, this one z axis, then this one is actually y axis, and this is y axis, this is z axis. No need to bother about x axis, we are not going to do anything on the x axis now. Before going to this discussion, I want to tell you one point here students. What is that? You see carefully. Already I have taken like this antenna x, y, z. Here I have taken one antenna like this. I told you the magnetic field pattern is proportional to sine theta, and the electric field pattern also proportional to sine theta, where theta is angle between the actually here point r comma theta comma pi is there. Theta is the angle between the z axis and the line drawn from origin to the field point. If you see carefully, this antenna rod was also parallel to the z axis. That means actually this theta is angle between this antenna rod and the line drawn from origin to field point. Because here in the derivation, this antenna rod length was in z direction only. So theta means angle between z axis and p and point p. That is the meaning in the coordinate system, spherical system. But here after doing derivation, here theta means that is the angle between antenna rod length and the line drawn from origin to the field point. That is why if you take a horizontal antenna like this, if you take horizontal antenna, so horizontal antenna, then here the meaning of theta is actually angle. This is 90 degrees only now also. This is point r comma theta comma pi. So this is actually 90 degrees only, dear student. This is theta only now also, but here you have to substitute electric field is proportional to sine of here theta means angle between antenna rod and the line drawn from origin to field point. So here this theta here is angle between antenna rod, that is this one, and the line drawn from origin to the field point. Now that angle becomes this one, so that is 90 minus theta I have to substitute. So if you substitute 90 minus theta, then electric field is proportional to cos theta. Conclusion is that we have studied already, if antenna rod is like that, then electric field proportional to sine theta, then the field pattern was figure of 8 like this. That field pattern has maximum value perpendicular to the antenna rod length. Here field pattern will be like this, dear student. That means you can easily understand this is sine theta pattern and this one is cos theta pattern, student. So this antenna rod is horizontal. Horizontal means parallel to xy plane. This is x, this is y, parallel to xy plane. Then that is called horizontal antenna. So this horizontal antenna electric field is proportional to cos theta. This antenna may be turned like this also. Then also electric field is proportional to cos theta only. If antenna rod is like this, electric field is proportional to sine theta, vertical antenna. Then horizontal antenna may be like this or may be like this. For horizontal antenna, it is electric field is proportional to cos theta actually. So if antenna rod is like this, you can see the length. But if antenna rod is like this, you can't see the length. Simply dot is shown. So dot means antenna is like this. That is also horizontal antenna. For this also electric field is proportional to cos theta only, students. So for this antenna or otherwise for this antenna, both are horizontal or otherwise parallel to the xy plane. So in that case, electric field proportional to cos theta, you have to remember, right, students? This one is the important point. You might have noted down this one. Now I am taking here one antenna element like this, that one like this. Second antenna element I am taking like this. Actually, they are like this, student. Lengths are there like this, like this. And third antenna element I will take here. Fourth one I will take here. Fifth one I will take here. Like this dash dash n number of antennas I will take, student. So here I am showing first dot. There one antenna is there. For that current I1 is equal to I0 at an angle of 0. This is actually, this current is in phasor domain. So this current is in phasor domain I1s. Actually in time domain, na student, it is like this. I1 of t is nothing but I0 into cos of omega t plus 0. That is the phase I1 of t is equal to in time domain. In phasor domain, cos omega t is reference. So I0 in I0 at an angle of 0 is taken. So this is the first antenna. So here first antenna, this is second antenna. Then the current is equal to I0 at an angle of alpha is taken. This is actually third antenna like this. Okay, here it is taken dash 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 dash. Here nth antenna is taken. So here I3 of S is equal to I0 at an angle of 2 alpha. Similarly, dash dash dash, this is what do you say, nth antenna, this one. So this is first antenna, this is second one, this is third one, dash dash dash. Now the distance between antenna elements is actually d, dear students. I will write here. So d is the distance between the antenna elements. Here first one, here second one, third one. So this distance is also d only, right? Here d is the distance between antenna elements. Total n elements are there. Now students, I want to tell you one statement, dear students. Why to use group of antennas? For example, let us say for single antenna gain is 10, but our requirement of gain is 100. Then you have to put so many antennas. In that way, then after putting so many antennas, gain is increased. That is one thing. For example, this single antenna gives radiation pattern like this. But my demand is I want radiation pattern only in one direction. This direction I don't want. Then if you take single antenna, then you can't get this type of pattern. So you have to put group of antennas. Then you have to give different phase angles, so that if current phase angle changes, then radiation pattern also changes. Then at some locations electric field adds. Then at some other locations electric fields are cancelled, so that you get this type of pattern. So conclusion is, if you want more gain, if you want a desired radiation characteristics like this, so in that case you need a antenna array, because single antenna cannot give desired gain, cannot give desired radiation characteristic. So desired radiation characteristic means I want only radiation in one direction, but with single antenna that can't happen. So if I take single antenna, it gives radiation pattern like this. We have seen already, we have drawn. Now I want only top side, but I don't want this side, but nothing can be done. That antenna gives that also. So for example, here only people are there to listen radio, but sending power this side is useless. It is wastage of power. It is better you turn this power that side, then it is more meaningful. That power goes for longer distances. So I will write that statement also. The purpose of the antenna array is to get the desired characteristics like required gain and like the radiation pattern in particular directions, etc., etc. So gain can be increased in particular direction, radiation pattern can be cancelled. Those things can be done using the antenna array. I will write that statement here. So students, now here total number of antennas are n here, n number. Okay. Now what we do here in the spherical coordinate system, this is actually point r comma theta comma pi. This is called far point. This is called far point. Here you want electric field at this location. Electric field is a function of r theta pi, this electric field vector. So this is the point p r theta pi. It is called far point. Here I want electric field r theta pi. Okay. First, let me write that antenna array is used to get required gain, comma desired means जैसा मर्जी है वैसा radiation pattern, desired radiation pattern, etc. Okay, etc. which cannot be obtained using single antenna. That is why with single antenna we cannot get them, students. That's why we need antenna array. That means group of antennas. Now I am doing here some rough work, student. Then you keep watching. Now here what is the total electric field intensity at this location? E total is equal to, electric field is linear. Find electric field at this location due to first antenna, call it as a E1. Then find electric field here due to second antenna current, call it as a E2. Then similarly, find the electric field at this location due to third antenna, call that as a E3 dash dash dash. Then for nth antenna, due to nth antenna electric field here is En. Then total electric field is sum of them. Then what we do, E1 you common. Then 1 plus E2 by E1 plus E3 by E1 plus dash 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 plus En by E1. So now this is E1 into, it is ratio, electric field by electric field ratio. This is called factor actually. Factor means no unit. So this is one factor. This is combination of ratios. This is one factor. Factor means no unit. This factor is coming because of group of antennas. That is why that is called group factor, or otherwise group other name is array. So that is called array factor. So this one is called this one together, this total called as array factor. What is this? Array factor. So dear student, short name of that is E1. That means total electric field is equal to this one, electric field due to single antenna. That you can't change that. For example, if antenna is like this, then that electric field is proportional to cos theta. If antenna is like this, electric field is proportional to cos theta because horizontal antenna. If electric field is like this, if antenna is like this, then that electric field is proportional to sin theta. Then this is actually array factor. So for example, this one E1 is electric field due to single antenna. E2 means electric field due to second antenna, like that. So small derivation is there for this. Now here if you apply common sense, that I was telling you, electric field due to single antenna, it has some equation. You can't change that equation. You can't do nothing there. You cannot do anything. So that means you cannot do anything here. But array factor, na, there you can change number of antennas. You can change angle of the input currents. You can change the current magnitude. So many things you can do. But anyway, here we will be taking same magnitudes of currents and same distance between the antenna elements. So this I want to tell you, our focus should be on array factor, because inside the array factor, number, number of antennas and the angle between current elements alpha, all terms come. If you change them, then this value is going to change. Then overall electric field value is going to be changed. Our focus is here array factor. Okay, students. Now array factor. This is the important discussion. Array factor. Uh, anyway, if you want, I will write like this, where E1 is proportional to cos theta. This is for horizontal antenna. Okay, that is just for your knowledge. That is, now array factor is equal to sin n psi by 2 divided by sin psi by 2, sin psi by 2, dear students, array factor. So this you have to remember, and here already it has a n. Now I am going to tell you what is psi. Psi is actually angle factor. We will see that how to write that situation to situation. You see that psi you have to write where psi is. Listen. Actually, this is far point. Far point means meaning is that if you draw the lines from here to here, all will be looking like a parallel lines. That is the meaning of far point. So this line is looking like this, a little straight. It should be a straight line hona hai ye, like this, and this is also like this. And you see here, if you draw a 90 degrees line from here to here like this, here 90 degrees is there, student, 90 degrees. 90 degrees is there. Then they should have same lengths here like this. They have same lengths here like this. Okay. Similarly, like this they are. Okay. So that means here to here lengths are same. Okay, students. Now this is called from here to here R, let us say. Then this is R. And this one is R1, let us say. Then R minus R, then R minus R1, there is some difference in the distance. So here this is a D, distance between antenna elements, and the angle between Z axis and line drawn from origin to this field point is actually, this is theta angle, student. This is also theta. Everything is theta here. Now this distance, this one, this distance actually, I will write this like this. This distance is touching means adjacent. So d cos theta it is, students. This one, d cos theta. 90 degrees na, opposite to 90 hypotenuse. Then here angle is touching this one. This is adjacent. Adjacent is equal to hypotenuse into cos of angle. Now I am asking one question, you have to answer. This distance from the second element to this field point is R1. Distance from first element to the field point is R. So the distance difference is R minus R1 is actually d cos theta. That means this antenna phase, otherwise I will do like this. We have seen that beta Z is a distance phase. Distance phase. Okay. For d is equal for d cos theta distance for d cos theta distance, the distance phase is equal to beta into d cos theta. Okay, this is another statement. This is first statement, this is second statement. For d cos theta distance, the distance phase is equal to beta into z actually. So here z is d cos theta. Now, because of distance change, there is a distance change between second antenna element and first antenna element. The phase is coming, phase difference is beta cos theta, students. Now already the second antenna element current phase angle is alpha for this 0. So in current also there is a phase difference. So second antenna current phase minus, observe carefully, always you have to calculate top antenna current phase minus bottom one is alpha. For example, here if you select this antenna, just above that antenna there is another one, phase of this is 2 alpha, minus phase of this is alpha. So the phase difference between current elements is alpha. So overall phase difference is total phase difference between second and first antenna, second comma first antenna elements is equal to, that is psi is equal to beta d cos theta plus alpha. That is that thing, students. So once again I am telling you how you calculate alpha while solving questions. You select two antennas, in them top antenna phase minus this antenna phase. That is the way you calculate. So that here psi is equal to total phase difference, that is beta d cos theta plus alpha, and the beta is nothing but 2 pi by lambda into d cos theta plus alpha. So here I will be writing lambda is equal to v by f. So d is the distance between, d is the distance between two antennas, distance between the d is the distance between two antennas, right? Two antenna elements, you say. Each antenna is called actually element here. So two antenna elements. Then d is that one. Then students, alpha is phase difference. Phase difference between currents of, the phase difference between currents of second antenna and first antenna. Like this I will write, so that later on you will be comfortable. Okay, this is alpha. Alpha, theta, theta I have to write. Theta. Listen carefully. Here, first antenna like this, from front dot, second antenna, third antenna. Antennas are on the z axis, so that is why z axis is called array axis. Array axis means the line on which antenna is present is called array axis. Okay, students. Now here, what is theta? Angle between array axis. Don't say z axis, because sometimes antennas are on the x axis, na. Then array axis is x axis. So you have to change the definition. Anyway, Now theta is angle between array axis and line drawn from origin to the field point. So theta is first I will write like this. The line on which antenna elements are present is called as array axis. Now theta is the angle between array axis. Here example here z axis. In this case it is z axis, student. It is now z axis in this case. But anywhere if antennas are on the x axis, then that is x axis. Theta is the angle between array axis and the line drawn from origin to field point. Okay, origin to field point. So we are generalizing the terms actually, dear students. We are generalizing. Next, actually, first antenna current magnitude is I1, second antenna current magnitude is I2, third antenna current magnitude is I3. Then that is called non-uniform array. But here we are taking I0, same currents, but progressive phase shift can be there. Then that is called uniform array. If current magnitudes are same, that is called uniform array. So here, if distance between antenna elements D1, D2, D3 like that, different distances are taken, then that is called non-linear array. But here we have taken distance between them D, D, D. So that is called linear array. So linear array means distance are same. Then uniform array means current magnitudes are also same. So linear and uniform array satisfies all of our requirements like gains, radiation characteristics. That is why we use linear and uniform array only. So I will write the definition also there. So here, if distance between antenna elements D is same, if the distance between antenna elements D is same, then it is same, then it is called as a linear array. Okay, that is the meaning of linear array. Next, if the current, I will write like that. Okay, if all antennas, all antennas have same current magnitude, but progressive phase shift, can be there, but progressive phase shift can be present, then it is called as uniform array. Same current magnitude. So here we have taken all antennas have same current magnitude called I0, that is nothing but maximum value of the current, and the progressive phase shift alpha is there, then that is called uniform array. That means we are talking of linear and uniform array. For that, actually, what do you say, array factor is n, where n is number of antenna elements. I will write it here if you want. So dear students, now let us talk of array factor. I told you, if you change alpha, if you change d, etc., then n number, if you change array factor value changes, then if array factor value changes, total electric field changes, then design change can happen. You can change the design by changing the parameters here. That is why we have to talk of array factor. You have to remember this one, right? Point by point we will discuss. So n means what here? Number of antenna elements. Dear students, here first one, I am writing note. First one, students, array factor already you have remembered. We will find like this. Array factor, when we will put psi 0, then what will happen? Let us see. Sin 0 divided by sin 0, that is actually not defined. So it is not defined. That means you have to go to L hospital rule. Now array factor is equal to, you differentiate numerator, that becomes cos n into psi by 2, then n by 2 you get, divided by once again cos psi by 2, once again you get 1 by 2. That means you get n of this one. Again you substitute psi is equal to 0. Now half gone, you get n into cos 0 is 1, this is 1, so ultimately you get n. This is the highest value, array factor maximum value. What is the meaning of this? Physical meaning, students. I told you that here total electric field is equal to E1 plus E2 plus E3 plus dash dash dash. Here you are giving currents and phased angles to the currents in such a way electric field due to each antenna adds. So E1 plus E1 plus E1 plus E1 all are in same phase. Then you common the E1, then you get E1 into n. That is the meaning of that. That is the highest value actually. So this is now we have to remember here one point. What is that point? Array factor maximum value is equal to n. That happens when psi is equal to 0. So you have to remember this one. Students, this is very important discussion, because later on to solve the questions. So what is happening here, I will tell you one time. Whenever you put psi 0, then array factor is maximum. What is the meaning of that? Let us see. For example, somebody asks you, that person want maximum electric field at theta is equal to 90. Then what you do? You want maximum electric field means this electric field should be maximum required. Then what you do? You make this array factor maximum value, then maximum multiplied with something is giving maximum. So if you want total electric field maximum, no, this array factor should be maximum. That means if anybody asks you electric field maximum is required at theta is equal to 90 degrees, na, then you have to substitute psi 0 here, psi 0, then theta 90 degrees you have to substitute, students. If anybody asks you maximum electric field is required at theta is equal to 45 degrees, na, then substitute theta is equal to 45. Here you can see maximum electric field is required at 45 degrees, na, student. Then this angle should be changed to 45 degrees. That means at this 45 degrees you need a maximum electric field. That means theta is equal to 45, you have to substitute. And also at the same time, if you want maximum electric field, array factor should be maximum. So whenever you put psi 0, then you get the array factor maximum. So for maximum electric field calculation, angle you put here, at which angle you want maximum electric field, then array factor should be maximum. Then from that you will be calculating alpha value. For example, if you get alpha 120, then you have to put here alpha 120, 2 times 120, like that you have to put. then automatically you get the maximum electric field there. So dear students, here array factor is maximum value is n when psi is equal to 0. This is standard one. Now anyway, here array factor if you want I will write. So array factor is equal to sin n psi by 2 divided by sin psi by 2. Already I have written there. So for the continuity purpose I am writing. Second one, students. Second one is normalized array factor. Normalized array factor AFN is defined as array factor normalized is equal to array factor divided by array factor maximum. So that array factor normalized is equal to this array factor 1 by n. This is the maximum value. Then array factor is sin n psi by 2 divided by sin psi by 2. So n psi by 2 divided by sin psi by 2, that is. So this is the array factor normalized value. So third one, nulls of array factor. My dear students, actually nulls of array factor is nothing but nulls of electric field. Null means 0. You can see here students, if array factor is 0 then electric field is also 0. That 0 is called a null actually. So nulls of array factor occur at whenever array factor is equal to 0. That implies array factor 0 means that is sin n psi by 2 divided by sin psi by 2 should be 0. That means sin n psi by 2 is 0. So sin n psi by 2 is equal to 0. So dear students, that happens whenever n into psi by 2 is equal to plus or minus k pi. Actually sin is 0 whenever angle is 0 degrees, pi degrees, etc., etc. But for k 1, 2, 3, 4 dash 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 you have to substitute. Okay, you should not substitute k 0 because if k 0 then psi 0, that is allotted for maximum. So k 0 for here k 0 for array factor maximum. So nulls won't come. That is why I have excluded that, student. Be careful. So k 0 not permitted. You write in your language, because k is equal to 0, substitute psi 0. Psi 0 means what discussion is going on. K 0 means here 0 comes. Then n psi by 2 is equal to 0 means sin 0. Sin 0 is 0. But you got that whenever k is equal to 0. But k 0 means psi 0. That is not permitted here. So student, k 0, then we get psi 0, that is allotted for array factor maximum. That is why you have to exclude here k 0. Okay students, don't confuse here, right? So these 3 points you remember. Array factor you have to remember. Array factor maximum value occurs whenever psi is equal to 0. Then if you want a highest electric field, then array factor should be maximum. Then array factor nulls occur at occur whenever n psi by 2 is equal to plus or minus k pi. K is integer varying from 1, 2, 3, 4, etc., etc. Okay.